Introduction number 7. Good day. Today we will talk about scientific method and research. Scientific method, the process of gaining knowledge about the universe through the observation of measurable evidence. Headline news: be wary, the media, not a great resource, exaggerate and oversimplify. Nutrition, a very young science new and conflicting studies reported daily. Always consider the following points: quality of the study and design of study, who funded the study. 1. Individual study versus meta-analysis. Meta-analysis, a review process that involves a statistical analysis of several previously published studies, providing quantification and the strongest evidence available on a topic. Often not put into perspective, study performed in a lab, but can it be generalized to the real world? 2 broad types of valid scientific research: study designs, observational, epidemiological, experimental. Observational research studies large populations to find relationships between 2 variables. Epidemiological research is usually observational. Study of the distribution and determinants of diseases or health outcomes in human populations. Examples: saturated fat intake and heart disease, sodium intake and high blood pressure, obesity and type 2 diabetes. Observational research. 2 main techniques used in epidemiological research: retrospective techniques. Compare diets of those with a disease to a similar group cohort of those without a disease. Prospective techniques. Diets of individuals without a disease are studied for years and then related to those who do and do not develop the disease. Observational research. It does show an important relationship between 2 variables, i.e. diet and health. It does not establish cause and effect relationship between the 2 variables. Experimental research. Essential to establishing a cause and effect relationship. Cause and effect: independent variable, cause, diet, dependent variable, effect, heart disease, randomized controlled trials, RCTs. Experimental research. Conditions for best experimental research: gold standard randomization of subjects, control, placebo, conditioned double-blind procedure. Experimental research. Studies on sports performance, mostly laboratory studies, some designed to mimic actual sports performance, but few studies during actual competition. Reading and interpreting a study abstract equals summary, introduction equals gives background, states purpose and hypothesis, methods equals how study was conducted, study design, who, participants. Inclusion, exclusion criteria: where, lab, clinic, field, what, how, treatment, materials, data analysis, results equals what was found, statistical significance, p-value, p less than 0.05, clinically significant. Conclusion equals what the results indicate, discussion equals insight, application, strengths and limitations, future research recommendations, references. Scientific method of research. Scientific research method: development of mathematical models, applying these methods to completing an MS thesis or a PhD thesis. Scientific method of research. 4 steps. If the experiments prove the hypothesis to be true, it becomes a theory, a law of nature. If the experiments prove the hypothesis to be false, the hypothesis must be rejected or modified. The scientific method used properly should give us predictive power to understand phenomena which have not been tested. Observation, an act of recognizing and noting a fact or occurrence, often involving measurement with instruments. Experiments performed in the laboratory. Experiments gained from knowledge of the literature. Hypothesis, tentative assumption made in order to draw out and test its logical or empirical consequences. Keys to implementation in your research. Good hypothesis can be tested with experimental calculation. This requires a lot of thought and reading. Leap from observation to hypothesis. It is worth the effort because after thinking this through, you are ready to go into the laboratory, which is the fun part of research. Experimental testing, to be assigned a standing or evaluation on the basis of tests. 2. To apply a test as a means of analysis or diagnosis, keys to implementation in your research. Good tests will prove or disprove your hypothesis. Experimental tests can be performed within the realm of computing, e.g., Covington model with calculations and predictions can serve as experiment and model. Consider all alternatives. Experiment may not disprove all, but may disprove only parts of your hypothesis. That is still alright to perform. Carefully note which aspects of your hypothesis this experiment will test. Consider the availability of instrumentation to perform your tests. Predictions to declare or indicate in advance, especially foretell on the basis of observation, experience, or scientific reason, keys to implementation in your research. Good predictions can also be tested against your hypothesis. Consider going back to the basics, textbook theory, to development of a mathematical model, construct which will help to make predictions about more systems than you can reasonably test. Mathematical models, empirical versus deterministic, keys to implementation in your research. All thesis experiments should have empirical models, at least. If do not have a mathematical model, only data, then we need to find an equation for which we can perform least squares fitting your data. My suggestion: if you run into an interesting hypothesis which can be tested via deterministic models, first principles approach, meet with IFM modeling faculty, Maynard E. Horn, Hegel or De Rosa, to discuss the hypothesis and modeling. Further suggestion: know what has been done by others. Do not reinvent the wheel unnecessarily. Understand your field. This qualifies you to make reasonable hypotheses about fundamental advances in the field. Do not strive to solve all problems in the field. Look for small advances in your field. Small advancements lead to critical developments. Prepare to report results even if hypothesis fails. False hypotheses are also advancements in science, and will save others time and money on repeating these experiments. Failed hypotheses should also be used to make suggestions for future directions, making you an expert since you can suggest new directions in your field. Goal: what is the scientific method? What does the scientific method assume? Does the scientific method work? What is not a scientific argument? Does astrology follow the scientific method? The scientific method: 1. Observe an event. 2. Develop a model or hypothesis which makes a prediction. 3. Test the prediction. 4. Observe the result. 5. Revise the hypothesis. 6. Repeat as needed. 7. A successful hypothesis becomes a scientific theory. Food science: throwing something together. Hypothesis or grandmother's time, tested recipe. Scientific theory. Repeatability: a successful theory is repeatable. By you. By anyone. Examples: cold fusion, 1989, ecstasy, science, 2003. Requirements: objective reality: we all see the same world. Constant laws of nature: what happens here, happens there. What happened yesterday will happen tomorrow. The cosmos is knowable. Does it work? Scientific method is a tool. Does this tool work? Life expectancy, mortality rate, are there better tools? Theory: so, a theory is a highly successful hypothesis. All hypotheses make predictions. All theories make predictions. All theories can be tested. Result: Any scientific theory is subject to change as our ability to make tests or make observations of a test result improves with time. Non-scientific theories make no predictions. Untestable can't be falsified. Non-scientific theories: car won't work. Aliens drained the battery. Spaghetti is bland. You were meant to eat bland food. Car won't work. Gods must be angry. Spaghetti is bland. At the instant of tasting, tongue is transported to alternate dimension where all flavors are rendered nullified. Happens instantaneously. Falsification: a real scientific theory tells you what observations are necessary to falsify it. Not so proponents of place on Mars moon hoax. Intelligent design astrologers. Second and third nature. As mentioned earlier, an information society is a means of getting information from one place to another. Hawke, 1997, p. 22. As technology has become more advanced over time, so too has the way we have adapted in sharing this information with each other. Second nature refers a group of experiences that get made over by culture. Hawke, 1997, p. 23. They then get remade into something else that can then take on a new meaning. As a society, we transform this process so it becomes something natural to us, i.e. second nature. So, by following a particular pattern created by culture, we're able to recognize how we use and move information in different ways. From sharing information via different time zones, such as talking online, to information ending up in a different location, sending a letter overseas. This has all become a habitual process that we, as a society, take for granted. Hawke, 1997, p. 21. However, through the process of sharing information, vectors have enabled us to spread information even further. Through the use of these vectors, information is able to move and then separate from the initial things that enable them to move. Hawke, 1997, p. 24. From here, something called third nature has developed. An extension of second nature. Third nature is in control of second nature. It expands on what second nature is limited by. It has the ability to mold information in new and different ways. So, third nature is able to speed up, proliferate, divide, mutate, and beam in on us from elsewhere. Hawke, 1997, p.25. It aims to create a balance between the boundaries of space and time. See second nature. This can be seen through the telegraph. It was the first successful technology that could send and receive information faster than a human being could move an object. Hawke, 1997, p.26. As a result, different vectors of people have the ability to not only shape culture, but create new possibilities that will ultimately shape society. Therefore, through the use of second nature and third nature, society is able to use and explore new vectors of possibility where information can be molded to create new forms of interaction. Hawke, 1997, p.28. Sociological uses. In sociology, informational society refers to a postmodern type of society. Theoreticians like Ulrich Beck, Anthony Giddens and Manuel Castells argue that since the 1970s a transformation from industrial society to informational society has happened on a global scale, 18, as steam power was the technology standing behind industrial society. So information technology is seen as the catalyst for the changes in work organization, societal structure and politics occurring in the late 20th century. In the book Future Shock, Alvin Toffler used the phrase super-industrial society to describe this type of society. Other writers and thinkers have used terms like post-industrial society and postmodern industrial society with a similar meaning. Related terms: A number of terms in current use emphasize related but different aspects of the emerging global economic order. The information society intends to be the most encompassing in that an economy is a subset of a society. The information age is somewhat limiting, in that it refers to a 30-year period between the widespread use of computers and the knowledge economy, rather than an emerging economic order. The knowledge era is about the nature of the content, not the socio-economic processes by which it will be traded. The computer revolution and knowledge revolution refer to specific revolutionary transitions, rather than the end state towards which we are evolving. The information revolution relates with the well-known terms agricultural revolution and industrial revolution. The information economy and the knowledge economy emphasize the content or intellectual property that is being traded through an information market or knowledge market, respectively. Electronic commerce and electronic business emphasize the nature of transactions and running a business, respectively, using the Internet and World Wide Web. The digital economy focuses on trading bits in cyberspace rather than atoms in physical space. The network economy stresses that businesses will work collectively in webs or as part of business ecosystems rather than as standalone units. Social networking refers to the process of collaboration on massive, global scales. The Internet economy focuses on the nature of markets that are enabled by the Internet. Knowledge services and knowledge value put content into an economic context. Knowledge services integrates knowledge management within a knowledge organization that trades in a knowledge market. In order for individuals to receive more knowledge, surveillance is used. This relates to the use of drones as a tool in order to gather knowledge on other individuals. Although seemingly synonymous, each term conveys more than nuances or slightly different views of the same thing. Each term represents one attribute of the likely nature of economic activity in the emerging post-industrial society. Alternatively, the new economic order will incorporate all of the above plus other attributes that have not yet fully emerged. Intellectual property considerations. One of the central paradoxes of the information society is that it makes information easily reproducible, leading to a variety of freedom, control problems relating to intellectual property. Essentially, business and capital, whose place becomes that of producing and selling information and knowledge, seems to require control over this new resource so that it can effectively be managed and sold as the basis of the information economy. However, such control can prove to be both technically and socially problematic. Technically, because copy protection is often easily circumvented, and socially rejected because their users and citizens of the information society can prove to be unwilling to accept such absolute commodification of the facts and information that compose their environment. Responses to this concern range from the Digital Millennium Copyright Act in the United States, and similar legislation elsewhere, which make copy protection, CDRM, circumvention illegal, to the free software, open source and copyleft movements, which seek to encourage and disseminate the freedom of various information products, traditionally both as in, gratis, or free of cost, and liberty, as in freedom to use, explore and share. Caveat: information society is often used by politicians, meaning something like, we all do internet now. The sociological term information society, or informational society, has some deeper implications about change of societal structure. Information system is the study of complementary networks of hardware and software, see information technology, that people and organizations use to collect, filter, process, create, and distribute data. The study bridges business and computer science using the theoretical foundations of information and computation to study various business models and related algorithmic processes within a computer science discipline. Computer Computer Information Systems. This is a field studying computers and algorithmic processes, including their principles, their software and hardware designs, their applications, and their impact on society, while it emphasizes functionality over design. Any specific information system aims to support operations, management and decision-making. In a broad sense, the term is used to refer not only to the information and communication technology, ICT, that an organization uses, but also to the way in which people interact with this technology in support of business processes. Some authors make a clear distinction between information systems, computer systems, and business processes. Information systems typically include an ICT component but are not purely concerned with ICT, focusing instead on the end use of information technology. Information systems are also different from business processes. Information systems help to control the performance of business processes. Alter argues for an information system as a special type of work system. A work system is a system in which humans and/or machines perform work using resources to produce specific products and/or services for customers. An information system is a work system whose activities are devoted to processing, capturing, transmitting, storing, retrieving, manipulating, and displaying information. As such, information systems interrelate with data systems on the one hand and activity systems on the other. An information system is a form of communication system in which data represent and are processed as a form of social memory. An information system can also be considered a semi-formal language which supports human decision-making and action. The history of information systems coincides with the history of computer science that began long before the modern discipline of computer science emerged in the 20th century. Regarding the circulation of information and ideas, numerous legacy information systems still exist today that are continuously updated to promote ethnographic approaches, to ensure data integrity, and to improve the social effectiveness and efficiency of the whole process. In general, information systems are focused upon processing information within organizations, especially within business enterprises, and sharing the benefits with modern society. Overview. Silver et al. 1995 provided two views on is that includes software, hardware, data, people, and procedures. A second managerial view includes people, business processes and information systems. The Association for Computing Machinery defines information systems specialists as focusing on integrating information technology solutions in business processes to meet the information needs of businesses and other enterprises. There are various types of information systems. For example, transaction processing systems, decision support systems, knowledge management systems, learning management systems, database management systems, and office information systems. Critical to most information systems are information technologies, which are typically designed to enable humans to perform tasks for which the human brain is not well suited, such as handling large amounts of information, performing complex calculations, and controlling many simultaneous processes. Information technologies are a very important and malleable resource available to executives. Many companies have created a position of Chief Information Officer, CIO, that sits on the executive board with the Chief Executive Officer, CEO, Chief Financial Officer, CFO, Chief Operating Officer, COO, and Chief Technical Officer, CTO. The CTO may also serve as CIO, Chief Information Officer, and vice versa. The Chief Information Security Officer, CISO, focuses on information security management. The discipline of information systems. Severalist scholars have debated the nature and foundations of information systems, which has its roots in other reference disciplines such as computer science, engineering, mathematics, management science, cybernetics, and others. Information systems also can be defined as a collection of hardware, software, data, people and procedures that work together to produce quality information. Information may also be given from the person or application. The impact on economic models. Microeconomic theory model. Clarification needed. Transaction cost theory. Clarification needed. Agency theory. Clarification needed. Differentiating is from related disciplines. Information systems. Relationship to information technology. Computer science, information science, and business. Similar to computer science, other disciplines can be seen as both related and foundation disciplines of IS. The domain of study of IS involves the study of theories and practices related to the social and technological phenomena, which determine the development, use, and effects of information systems in organization and society. But, while there may be considerable overlap of the disciplines and the boundaries, the disciplines are still differentiated by the focus, purpose, and orientation of their activities. In a broad scope, the term information systems is a scientific field of study that addresses the range of strategic, managerial, and operational activities involved in the gathering, processing, storing, distributing, and use of information and its associated technologies in society and organizations. 32. The term information systems is also used to describe an organizational function that applies its knowledge in industry, government agencies, and not-for-profit organizations. 32. Information systems often refers to the interaction between algorithmic processors and technology. This interaction can occur within or across organizational boundaries. An information system is the technology an organization uses and also the way in which the organizations interact with the technology and the way in which the technology works with the organizations. Business processes. Information systems are distinct from information technology. It's in that an information system has an information technology component that interacts with the processes components. One problem with that approach is that it prevents the IS field from being interested in non-organizational use of ICT, such as in social networking, computer gaming, mobile personal usage, etc. A different way of differentiating the IS field from its neighbors is to ask which aspects of reality are most meaningful in the IS field and other fields. This approach, based on philosophy, helps to define not just the focus, purpose and orientation, but also the dignity, destiny and responsibility of the field among other fields. Types of information systems. A four-level pyramid model of different types of information systems based on the different levels of hierarchy in an organization. B. Classic view of information systems found in the textbooks in the 1980s was of a pyramid of systems that reflected the hierarchy of the organization. Usually transaction processing systems at the bottom of the pyramid, followed by management information systems, decision support systems, and ending with executive information systems at the top. Although the pyramid model remains useful, since it was first formulated, a number of new technologies have been developed and new categories of information systems have emerged, some of which no longer fit easily into the original pyramid model. Some examples of such systems are data warehouses, enterprise resource planning, enterprise systems, expert systems, search engines, geographic information system, global information system, office automation. A computer-based information system is essentially and is using computer technology to carry out some or all of its planned tasks. The basic components of computer-based information system are Hardware. These are the devices like the monitor, processor, printer, and keyboard, all of which work together to accept, process, show data and information. Software are the programs that allow the hardware to process the data. Databases are the gathering of associated files or tables containing related data. Networks are a connecting system that allows diverse computers to distribute resources. Procedures are the commands for combining the components above to process information and produce the preferred output. The first four components, hardware, software, database and network, make up what is known as the information technology platform. Information technology workers could then use these components to create information systems that watch over safety measures, risk and the management of data. These actions are known as information technology services. Certain information systems support parts of organizations, others support entire organizations, and still others support groups of organizations. Recall that each department or functional area within an organization has its own collection of application programs or information systems. These functional area information systems face as supporting pillars for more general is namely business intelligence systems and dashboards. Citation needed. As the name suggests, each phase supports a particular function within the organization, e.g., accounting is finances, production, operation management, POM, is, marketing is, and human resources is. In finance and accounting, managers use IT systems to forecast revenues and business activity, to determine the best sources and users of funds, and to perform audits to ensure that the organization is fundamentally sound and that all financial reports and documents are accurate. Other types of organizational information systems are phase, transaction processing systems, enterprise resource planning, office automation system, management information system, decision support system, expert system, executive dashboard, supply chain management system, and electronic commerce system. Dashboards are a special form of IS that support all managers of the organization. They provide rapid access to timely information and direct access to structured information in the form of reports. Expert systems attempt to duplicate the work of human experts by applying reasoning capabilities, knowledge, and expertise within a specific domain. Information systems career pathways. Information systems have a number of different areas of work. Is strategies, management is development, is iteration, is organization. There is a wide variety of career paths in the information systems discipline. Workers with specialized technical knowledge and strong communication skills will have the best prospects. Workers with management skills and an understanding of business practices and principles will have excellent opportunities, as companies are increasingly looking to technology to drive their revenue. Information systems development. Information technology departments in larger organizations tend to strongly influence information technology development, use, and application in the organizations, which may be a business or corporation. A series of methodologies and processes can be used to develop and use an information system. Many developers have turned and used a more engineering approach such as the System Development Lifecycle (SDLC), which is a systematic procedure of developing an information system through stages that occur in sequence. An information system can be developed in-house within the organization or outsourced. This can be accomplished by outsourcing certain components or the entire system. 37. A specific case is the geographical distribution of the development team, offshoring, global information system. A computer-based information system, following the definition of Langfors, is a technologically implemented medium for recording, storing, and disseminating linguistic expressions. as well as for drawing conclusions from such expressions, which can be formulated as a generalized information systems design mathematical program. Geographic information systems. Land information systems and disaster information systems are also some of the emerging information systems, but they can be broadly considered as spatial information systems. System development is done in stages which include problem recognition and specification, information gathering, requirements specification for the new system design, system construction, system implementation, review and maintenance. Information systems research. Information systems research is generally interdisciplinary, concerned with the study of the effects of information systems on the behavior of individuals, groups, and organizations. Hevner et al. 2004 categorized research into two scientific paradigms, including behavioral science, which is to develop and verify theories that explain or predict human or organizational behavior and design. Science, which extends the boundaries of human and organizational capabilities by creating new and innovative artifacts. Salvatore March and Gerald Smith proposed a framework for researching different aspects of information technology, including outputs of the research outputs, and activities to carry out this research activities. They identified research outputs as follows: constructs, which are concepts that form the vocabulary of a domain. They constitute a conceptualization used to describe problems within the domain and to specify their solutions. A model, which is a set of propositions or statements expressing relationships among constructs. A method, which is a set of steps, an algorithm or guideline, used to perform a task. Methods are based on a set of underlying constructs and a representation, model, of the solution space. An instantiation is the realization of an artifact in its environment. Also, research activities including build an artifact to perform a specific task, evaluate the artifact to determine if any progress has been achieved. Given an artifact whose performance has been evaluated, it is important to determine why and how the artifact worked or did not work within its environment. Therefore, theorize and justify theories about IT artifacts. Although information systems as a discipline has been evolving for over 30 years now, the core focus or identity of his research is still subject to debate among scholars. There are two main views around this debate. A narrow view focusing on the IT artifact as the core subject matter of his research, and a broad view that focuses on the interplay between social and technical aspects of IT that is embedded into a dynamic, evolving context. A third view calls on his scholars to pay balanced attention to both the IT artifact and its context. Since the study of information systems is an applied field, industry practitioners expect information systems research to generate findings that are immediately applicable in practice. This is not always the case, however, as information systems researchers often explore behavioral issues in much more depth than practitioners would expect them to do. This may render information systems research results difficult to understand and has led to criticism. To study an information system itself, rather than its effects, information systems models are used, such as EATPUT. The International Body of Information Systems Researchers, the Association for Information Systems, ASH, and its Senior Scholars Forum Subcommittee on Journals, the 23rd of April 2007, proposed basket of journals that the ASH deems as excellent and nominated. Management Information Systems Quarterly, MISQ, Information Systems Research, ISR, Journal of the Association for Information Systems, JAIS, Journal of Management Information Systems, JMIS, European Journal of Information Systems, EJIS, and Information Systems Journal, ISJ. Components. The 5 components that must come together in order to produce a computer-based information system are 1. Hardware. The term hardware refers to machinery. This category includes the computer itself, which is often referred to as the Central Processing Unit, CPU, and all of its support equipment. Among the support equipments are input and output devices, storage devices, and communications devices. 2. Software. The term software refers to computer programs and the manuals, if any, that support them. Computer programs are machine-readable instructions that direct the circuitry within the hardware parts of the system to function in ways that produce useful information from data. Programs are generally stored on some input-output medium, often a disk or tape. 3. Data. Data are facts that are used by programs to produce useful information. Like programs, data are generally stored in machine-readable form on disk or tape until the computer needs them. 4. Procedures. Procedures are the policies that govern the operation of a computer system. Procedures are to people what software is to hardware, is a common analogy that is used to illustrate the role of procedures in a system. 5 people. Every system needs people if it is to be useful. Often the most overlooked element of the system are the people, probably the component that most influence the success or failure of information systems. Medical library professionals are partners on the healthcare team, playing vital roles in the delivery of healthcare, the conduct of medical research, and the education of health professionals. Medical library staff members are also instrumental in providing high-quality health information to the general public. Medical librarians are leaders in applying and promoting technology for the dissemination of information and the development of knowledge. Pioneers in the use of data processing, online interactive searching, electronic mail, internet access, and high-performance computing and communications. They are currently using their expertise to enhance access to health-related information on the web. Given this background, medical library jobs require skills somewhat similar to information technology, its positions found in the general marketplace. The objectives of this study were to provide an analysis of the job content and job designs of medical library positions compared to the content and design of information technology positions in general industry. Provide a complete analysis of the compensation of medical library positions compared to the compensation of the appropriate information technology positions in general industry. Identify common issues impacting medical libraries' abilities to effectively attract, retain, and compensate medical library staff with IT-related backgrounds. This study provides data from both the hospital library and the academic health sciences library settings. The study provides data that assists in determining the value placed on information technology functions through compensation. It shows whether librarians performing IT roles are compensated below, equal to, or above IT staff performing the same roles. The ultimate goal is to have data to support appropriate salaries for librarians. In turn, these salaries will help attract and retain employees in those hard-to-fill and key IT positions. The Medical Library Association, MLA, has already taken steps toward this goal. In 1997-1998, the MLA Status and Economic Interests of Health Sciences Library Personnel Committee, SEIC, oversaw the development of sample job descriptions for positions in medical libraries and information centers. Additionally, since 1983, MLA has conducted periodic salary surveys of its medical librarian members. The 6th Triennial Salary Survey conducted in 1998 is available on the members portion of the MLA website. Methodology staff from the Hay Group and MLA used the following approach in conducting this project. Project planning. Data collection. The Hay Group and MLA met to plan the project's roles, accountabilities, and timetables, so that there was consensus on the scope of the project as well as the project plan. In order to support a comprehensive data submission kit and analysis, we collected background materials from MLA to support the study, including previous and current compensation surveys, available information technology surveys, current medical library position descriptions, job understanding, a critical step in determining appropriate comparisons of medical library positions with information technology positions was gaining a detailed understanding of the content of these jobs. In this phase, we developed survey job models for 14 core medical library positions. We used current MLA survey job descriptions as a basis for these descriptions. These job models, we developed a data submission document that gathered relevant information concerning compensation, job design, and work environment issues for IT-oriented medical library positions. A section of the data submission document is represented in Appendix B. Data collected included demographic information, e.g., type of organization, size of organization, location, employee education level, etc. Compensation-related information, e.g., actual base salary paid as of March 2000, job design information, e.g., percent of time spent in IT-related work, accountability for managing people, typical functional responsibilities of positions, typical self-reported job titles, nature of information systems support, e.g., in-house, parent organization, external contractors, etc., attraction, retention, and compensation issues related to staff with IT-related skill sets, typical education and skill backgrounds of medical library employees. Thank you for attention.